Hello class, today we're going to talk about potential energy and types of bonds. Our objectives for today are going to be looking at ions and how they're forming between molecules. We're also going to learn about the properties for bonding and how they are in these type of bonding mechanisms. So the first thing is the octet rule. The octet rule, by definition, is when you're trying to make 8 electrons in the highest valence shell, for covalent bonds or for ionic bonds, they are going to be stable because they are going to fill that last shell. And we want to have atoms that are stable because they want 8 electrons for that. They're also going to be either gaining or losing electrons to fill that to form a noble gas configuration. And there are a couple of different types of chemical bonds that we find. Generally, you're going to find ionic, covalent, and metallic. Ionic is when you transfer electrons, covalent is when you're sharing, and metallic is when you're going to have that sea of electrons in there. So the attraction between these bonds is going to be determined by how these electrons are being transferred. Generally, they're going to have chemical bonds that you can have, and this electrostatic attraction between these bonds is going to be called a covalent bond, where you are sharing those electrons. Now, electronegativity is going to really depend upon the location of that element on the periodic table. Generally, electronegativity increases left to right, and they're going to decrease top to bottom. And the reason you're going to have that is because certain elements are going to want more electrons, and certain elements are going to be labeled ionic, polar, or non-covalent polar are going to be shared unequally. So, for example, fluorine is the most electronegative element, followed by chlorine and oxygen. Now, there's going to be something special about krypton and xenon because these are technically have a full shell, but they also have the ability under certain conditions to attract electrons as well. Metallic bonding is going to be when you have a sea of electrons, atoms that are being in between the positive charges of the metal. And these electrons are moving, and it occurs generally with metal atoms because they have low electronegativities and also delocalized electrons. Atoms also are going to have positive and negative attraction between these atoms, and the reason is because these electrons are delocalized. So a couple of properties of metals is that they have thermoconductivity, electroconductivity, malleability. They can form wires, inductility, and they also have a shiny texture. And generally, they are going to be found in these metals. The reason is because they actually have high melting and high boiling points for specific bonds, indicating that they are generally going to be very difficult to break down because of this attraction that we have. Also, metals are good conductors of heat and electricity, and they're also shiny and lustrous. Most importantly, though, is that they have low ionization energies and very low electronegativities because they tend to give their electrons around, or would like to have them move around in that. Now, metallic character is going to be increasing from right to left, while nonmetals are going to be located on the right side. They tend to lose electrons as you're going towards the left-hand side, and generally more metallic characteristics are going to be at the bottom of the periodic table because they tend to lose electrons. While going from left to right, there's a higher force of attraction between these positively charged atoms with their electrons, which eventually creates a nonmetal. And generally, it's going to be primarily in ionic bonds where you're going to find these metals. And we're going to talk about metal bonding later, but for ionic bonding, generally you're going to have a metal and a nonmetal, and you're going to be transferring electrons based off the differences in electronegativity. So opposite charges are going to attract, and generally you're going to have a metal with a nonmetal. You're also going to have very low electronegativities and a complete transfer of electrons, indicating that there's a positive charge on the cation and a minus charge on the anion. And this results in a very strong force of attraction. So think of all your ionic bonds like salt as an example, being extremely strong and very difficult to break. Now, a couple of properties for ionic species is that they are conduct electrical current only when they're dissolved in water, but they will also in a molten state, or in a molten state, they're going to be able to do that where the ions are moving around. But in their crystal state or crystalline structures, they are not going to conduct electrical current. And the reason is because of the strong attraction between the ions. They also have high melting and high boiling point in their solid form. And they're generally very poor conductors of electricity, and because their electrons are locked in. They also tend to be very hard and brittle, which means they're not malleable or ductile like metals, like pure metals. And the reason, again, is because they're kind of stuck in that crystal. Covalent bonds are going to be a shared electrons. They're going to be between a metal and a metalloid. They're also going to be polar covalent and non-polar covalent. So as an example right here, we have some sharing of electrons between fluorines and water, which water we already know is polar, and then fluorine is non-polar. And a couple examples of polar, non-polar, you can see from the picture right here, we have polar covalent being molecules that are shifted towards one side. They're generally going to be more negatively charged, while pure non-polar covalents are going to be more equally shared. And you're going to have differences in electronegativity for polar covalents. And this is really due to the fact that they have high electronegativities differences. So for something that has like a high, like a chlorine, for example, it's going to pull those electrons towards one side, creating a delta charge, while a pure non-polar covalent would not have that. Some very special properties about them. Generally, they're going to, be, as an example, plastic bottles. Diamonds are covalent network. They're very high melting points. Crystals, they generally are going to have very low boiling points and very low melting points. They're also going to have poor conductors of electricity because they have localized electrons, and they tend to be soft and brittle. Generally, they're also going to be solids or liquids at room temperature gas. So here are the differences for electronegativity. Now, you do not have to memorize electronegativity differences, but you do have to know the differences between polar and non-polar. For example, something that has a greater value of 1.8 generally is going to be on the ionic side. Anything that's lower than 0.4 would be non-polar. Anything in the middle would be polar covalent. And these are called electronegativity differences. And the reason is because of the fact that you have a molecule that is more electronegative and you subtract that to get your value. And so as an example, let's take a look at this chart. You probably want to pause this video, look for some electronegativity values, fill them in, and then tell me whether it's polar or non-polar. So for example, if I take something like a CH, I look at the electronegativity difference. If it's less than 0.4, it will be nonpolar, and anything in between, you can kind of look at that chart again. Go ahead and pause this video to try to see if you can do some of these, and then we'll check back here with their answers. So if I take a look at the bonds in order of increasing polarity, we'll find that it's possible that you can complete this only if you know that the values are going to be based off of the same carbon. So for example, if we take a look at these elements, the only thing that's different here is going to be the second element. And so we already know that electronegativity differences will be your trends based off the periodic table. And on the right hand side, you can kind of take a look at a couple of examples, nonpolar, ionic. So ionic generally is going to have a metal, non-metal. Metallics are going to have pure metals like copper and zinc. And these are going to generally be classified as either ionic or metallic, and your nonpolars are the ones with the same element. Let's talk about intramolecular forces. So intramolecular forces are forces between molecules. If you take a look at this water molecule right here, it has a force of attraction between H and O, and that's called a hydrogen bond. And that bond is fairly weak. You can disrupt it very easily with heat. So intramolecular force is a bond between a molecule or a compound. And sometimes you're going to get things like nonpolar and polar molecules that are going to be attached themselves to other molecules. And because of that, they will actually have a force of attraction that's going to hold that molecule together. And usually it's going to be for like a state of matter. All right, in summary, you need to know a couple of things. The electronegativity generally increases left to right and decreases down a group, very similar to ionization energies. Coulomb's law is a great way to explain electronegativity, ionization values, so be sure to check those out. Valence electrons are going to be used for covalent bonding, and generally you're going to have higher electronegativity differences for different bonds, and the differences for polarity are going to really depend upon whether something's ionic or covalent. We also talk about delocalized and localized electrons, and these are going to be in metal atoms where they tend to be delocalized, but they're more localized in covalent bonds and ionic bonds.